Good morning, everybody. I'm Luca Vecchiato, PhD student in Industrial Engineering at the University of Padua. The work I present deals with the in-situ fatigue growth monitoring of a single-edge crack propagating run bars by means of the direct current potential drop method. The first question to be answered is why study run bars weakened by a single-edge crack? There are many reasons. The most important one is that they have many applications in engineering. They are quite common and widespread geometry. Moreover, the ASTM E647 suggests them for studying fatigue crack propagation on small cracks. The most important drawback of this geometry is that there is no optical access to the crack front. And so for studying crack growth, it is necessary to adopt non-visual experimental technique among all the direct current potential drop method. This method consists in imposing the flowing of a constant electrical current through the specimen and by measuring the potential drop between 2 points on the specimen itself. By entering in a proper calibration curve with the potential drop, it is possible to evaluate the crack size during the propagation. So it is quite easy to observe that the DCPD, the sensitivity of this method is quite depending quite so much on the shape of the calibration curve. So the aim of this work is trying calibrating and fine-tuning the DCPD setup for this kind of specimen. At this point, the question was how to evaluate the performances of a DCPD setup for comparing different setups. Aronson and Ricci proposed 4 parameters. The first is the measurability, which means the magnitude of the measured signal. The second is the sensitivity, which is the rate at which the signal changes with the crack size. The third is the reproducibility, which gives information about the insensitivity of the signal to unavoidable positioning errors of the probes. And the last is the accuracy, which gives information about the degree at which the calibration curve is representative of the real crack size and shape. In mathematical terms, the measurability can be evaluated by maximizing the potential drop value. The sensitivity by maximizing the derivative of this signal with respect to the crack size. Instead, the reproducibility by minimizing the changes of the signal with respect to the position of the potential drop probe. And at last, the accuracy can be evaluated by comparing the estimated value of the potential drop with respect to the experimental one. In this work, we performed the electrical finite element analysis to check the effects of the current and potential drop probes in the terms of measurability, sensitivity, and reproducibility, while at last, experimental tests have been performed for studying the accuracy. So, starting from the electrical finite element analysis, it requires an input to the specimen geometry, the material properties, the crack path, and information on the DCPD setup. And they give us, as an output, the different calibration curves for different DCPD setups to be evaluated in terms of measurability, sensitivity, and reproducibility. In this work, a cylindrical specimen with a semi-elliptical edge crack has been studied, and the materials were chosen to be equal to a medium carbon steel with an electrical resistivity of 20 times 10 to the power of -8 ohm per meter at room temperature. About the crack path, according to the literature, it has been assumed the crack propagates with a semi-elliptical arc shape. In the literature, there has been studied and proposed many criteria for studying crack growth for such specimen geometry, and among all, reported the ISOK1 criterion, the formal model, a model based on Paris-Erdogan law. Being not the aim of this work, predicting the crack path, but studying the measure of the DCPD measure on such specimen, it has been assumed that the crack propagates according to the ISOK1 criterion, and structural 3D finite element analysis by means of the peak stress method has been performed to define the crack path which satisfies this criterion. According to Levin and Royer, the ISOK1 criterion assumes that the crack shape changes with an aspect ratio which guarantees a constant value of the stress intensity factor along the crack front. In this work, The corresponding crack path has been evaluated adopting the peak stress method, which is an engineering tool for rapid estimation of notch stress intensity factors using just a novel finite element stress at the notch tip. In the reported expression, KFE star is a calibrated constant. D is the average size of the finite elements, and lambda is the stress singularity degrees. The crack path and the structural analysis have been performed adopting two different boundary conditions, one of which, sliding clamp, would simulate the effect of rigid machine clamps. As a result, it was possible to obtain the crack path, the aspect ratio C over A versus the normalized crack depth, which correspond to the ISO K1 criterion. And it was also observed that it was almost the same for the two studied different boundary conditions. The last parameter to be analyzed was the DCPD setup, so the position of both the current and the potential drop probe. For doing this, the finite element models have been realized according to the reported images, so taking advantage of ZX symmetry plane, half of the specimen was realized. The current was injected in four different manners. The first one was a remote current input, in which the current was injected from the specimen ends. The second one was a local current input, in which the current was injected on the cylindrical surface on the crack symmetry planes. And the third model was adopted to check the effect of the actual distance of the potential of the current probe with respect to the crack plane distance. And the last analysis was performed to check the effect of the angular position of the current probe. So the current probe was located at an angular position theta I equal to 50 degrees. At last, as an output, the potential drop value was measured all over the cylindrical surface of the specimen as a function of the angular coordinate theta PD and of the axial coordinate ypd. For the sake of brevity, results of the finite element analysis have been reported just for the remote current input and for the local current input with the current probe at an angular position equal to 50 degrees for a fixed crack size. Results show the effect of the potential drop probe's position as a function of their actual distance ypd and their angular position theta pd on the measurability, sensitivity and reproducibility, which has been evaluated as the derivative of the potential drop value with respect to the actual position of potential drop probes or the angular position of the potential drop probes. In general, the sensitivity is higher whenever the potential drop probes are located as close as possible to the crack plane, so YPD is as low as possible. And whenever the angular position is within the cracked surface, so between plus or minus theta PD. For the same region, the reproducibility assumes the highest value also. In general, it was possible to observe that the potential drop probe should be located as close as possible to the crack plane. In terms of angular position, that is a matter of choice. Locating on the symmetry plane the potential drop probes, the reproducibility is higher, where locating the potential drop probes as close as possible to the crack tip, so theta PD tending to theta B, is it possible to obtain the highest value of the sensitivity, so that's a matter of choice. To study the effect of the position of the current probes, it was fixed the position of the potential drop probes. In particular, the first configuration chosen was the most reproducible one, so locating the potential drop probes on the crack symmetry plane. And the second one was the most sensitive one, so locating the potential drop probe as close as possible to the crack tip whenever the crack is as a normalized crack depth of 0.3. It can be observed that in general considerations are the same, so the sensitivity and the measurability are higher whenever also the current probe are located as close as possible to the crack tip in general. So as in this example, whenever the crack tip reaches the position of potential drop probes, the sensitivity assumes the maximum values and then tending to the values of that they assume whenever the potential drop probes are located on the crack symmetry planes. The last parameter to be analyzed was the accuracy, and for doing so, fatigue test was performed. As briefly discussed before, evaluating the accuracy of a DCPD measure means comparing the estimated value of the potential drop with the experimental one. So for doing this, crack probe tests have been performed with the in-situ DCPD monitoring, so it was possible to obtain the experimental value of the potential drop as a function of the number of cycles. For having the experimental value of the potential drop compared with the real crack size and shape, some overloads have been introduced over the constant amplitude fatigue test for benchmark in the crack front and obtaining experimental calibration curve for the potential drop method. From the benchmarked crack front, it was possible to realize dedicated finite element analysis so as to obtain the estimated value for the potential drop to be compared at last with the experimental one so as to evaluate the accuracy of the measure. The experimental tests were performed adopting a cylindrical specimens with a straight front at the crack starter notch. The specimens were tested with the constant amplitude loads and with overloads, 10 cycles of overloads every 25,000 cycles of constant amplitude. The overloads were applied at a smaller load range, stress range, but a higher load ratio. The potential drop value were measured thanks to a clip-on gauge-like device designed and realized for the purpose of these tests, in order to both injecting the current and measuring the potential drop as close as possible to the crack tip. So according to the most sensitive configuration we have seen before. The output of this device and of the DCPD device was the potential drop signal, the main potential drop signal, and a reference one which is which is used normally for temperature compensation. The temperature compensation is performed by simply evaluating the ratio between these two signals, so the blue and the orange one. Here we are seeing an example relative to the specimen number 3. The image report the fractography of the fractal surface of the specimen, and this chart report instead the potential drop value as a function of the number of cycles. In blue the main signal, in orange the reference signal, and in black the normalized one, so the ratio between them. From fractography and the best fit in MATLAB, it was possible to obtain the change of the aspect ratio with respect to the normalized crack depth for each benchmarked crack front. Then combining the DCPD signals and this result, it was possible to obtain the experimental DCPD calibration curves both for the normalized signal in black and for the main signals in blue. Then, by performing dedicated finite element analysis, it was possible to check the differences between the estimated values of the potential drop and the experimental one. Interestingly, the accuracy found on a total of 9 specimens was quite good for small crack size, for A over D smaller than 0.3. The errors was in the order of 10%. For greater crack size, the error was on the average on about 10 to 15%, but sometimes was up to 40 to 50%. So coming to the conclusion, electrical finite element analysis have been performed to investigate the effect of both the current and the potential drop probe's position on the performances of the DCPD method applied to single edge crack round bars. The evaluation was performed in terms of measurability, sensitivity, and reproducibility. The crack probe applied for doing this was assumed to be according to the ISO-K1 criterion. And for evaluating the corresponding crack path, the big stress method was applied for the estimation of the stress intensity factors. Electrical finite element analysis showed that the highest value of the sensitivity can be obtained by locating both the current and the potential drop probes as close as possible to the crack tip, and the contrary, this position leads to the lowest value of the reproducibility. At last, the accuracy of the numerical analysis has been checked against experimental results, and for doing this, a clip-on gauge light has been designed and realized to both injecting the current and measuring the potential drop as close as possible to the crack plane, the crack tip. So that's all, and I really want to kindly thank you for your attention.